In the last lecture, we saw the propagation of waves, particularly the surface gravity waves or surface water waves. And there we assume the wave to be propagating continuously without breaking, right? And we saw two different kind of waves. So we derived the solution for the surface waves, and then we applied the solutions to deep water waves and shallow water waves, and we tried to understand their behavior, right? But in both the cases we assume the wave to be stable. Okay, and here in today's lecture we are trying to see what happens if there is instability in a wave. Okay, so here the first two images that you see are from the last lecture, right, where we, in this case, let's assume that we dropped a stone. If you dropped a stone, it created a wave, right? And this wave is assumed to be stable. And then in case 2, the wave that you see here, right, these are waves generated due to wind at the top. Right, so what's happening here is there is wind flow on top of water, and that is creating these waves. Whereas in the left hand side, in case 1, the wave was created because some object was dropped into it, right? So in case of waves getting generated because of wind velocity, it may also become unstable with time, with depending on the wind speed, right? And so what we see here is stable case, but there are these two cases which do not look very stable. Okay, so these are unstable waves, and what do you see exactly here is the waves that you can see, it's actually breaking, it is overturning, right? As you can see, this is not moving smoothly. So these waves that you see in bottom two images are because the waves are unstable, and in these cases particularly maybe the amplitude is much greater than the stable amplitude or critical amplitude, or the wavelength is very small compared to the stable wavelength, right? Whereas in upper case, for example here, the wavelength is quite large and amplitude is very small, such that the wave is still stable. Okay, but in case 2, the wavelength is very small and amplitude is very large, and that is making the waves unstable. Okay, and what we studied in the last lecture is for the stable cases, not for the unstable cases. So what happens? Why exactly this kind of waves become unstable? So let's try to understand that in more detail. So let's consider this case when we have two different fluids. Here we will assume that this is air, and the lower layer fluid is water. Okay, so for the upper layer there is rho 1, that is the density, rho 1, and for the low and also the velocity is, let's say, u1, whereas for the lower layer density is rho 2, which is greater than rho 1, and you have velocity u2 which is not equal to u1, so it has different velocity. So now there is a shear force or shear flow in the system because these two fluid layers are moving with different velocity, right? And what exactly is the shear flow? So whenever there is velocity gradient in the transverse direction, okay, and what is the transverse direction here? So we are assuming that this is the major direction of the flow, like both the fluids are moving in this direction horizontally. So in this case, what you see horizontally is the longitudinal direction, and what you see vertically is the transverse direction. Okay, so this one is transverse direction, and this is longitudinal. right? So when the majority of velocity is in a particular direction, that is called longitudinal, and the direction normal to the primary flow is known as the transverse direction. And when there is velocity gradient in the transverse direction, that is also tangential to the flow direction, in that case the flow is called a shear flow, right? And in this case we have this condition that u1 is not equal to u2. So when you go in vertical direction, which is tangential to the actual flow direction, right, there is difference in velocity, and that difference in velocity is bringing a shear flow. Okay, so what happens in case of shear flow is, as we can also see in this right side image, it actually creates this wave. Okay, that is something we also saw in case of this wave that we studied in the last lecture, right? These waves are getting created because of the shear flow. But when there is very large shear flow, when the value is small, waves are stable. But when the shear flow increases in magnitude, actually what happens is the magnitude of this wave, amplitude of this wave increases, and wavelength decreases, okay, with more and more velocity. So when this amplitude increases, there is greater and greater sudden change in the pressure between these two layers, and that brings instability in the system. And what happens is, whenever this amplitude becomes much larger, it becomes so unstable that it actually tries to overturn. Basically it tries to flow in horizontal direction rather than simply coming down. Okay, so it gets sort of both the longitudinal velocity and transverse velocity. Likewise, the trough of the wave actually also moves in the other direction. So one is, you can see, it's basically it has got a moment, uh, and other one also got a moment in same direction, I mean moment along the same axis, whereas the actual velocity is in the right side direction for the upper wave, in left side direction for the lower wave, right? And that creates this overturning of the wave. And if you go further and further, you can see it becomes so unstable that this wave will simply break here and it will come and mix in this particular region. Okay, so this part, now what you see here, this will completely mix with each other. So there will be air getting trapped inside water. Eventually that will come out, but for the moment it will get trapped. And now let's assume that these two fluids are miscible in nature. Instead of air and water, we consider two fluids which are miscible in nature. In that case, this will lead into a lot of mixing between these two fluids at the interface, which in the beginning we assume that this was a sharp interface. As you can see, there is no mixing between these two fluids, but because of the wave, because of this overturning of the wave, there is a lot of mixing that is coming into picture, right? And likewise, there is another case which can be considered as a shear flow. So in case 2, we have the upper fluid moving to the left and bottom fluid moving to the right. So again, there is change in velocity from one layer to the other. And whenever there is this shear flow, when velocity is changing in the transverse direction, there will be instability. As you can see, wave started getting created, and eventually there is this overturning, right? And this makes the wave unstable. Okay, so this instability in wave is actually not only a theoretical phenomena, but it also happens in nature very often, right? And as in case of ocean, we have already seen some images where these waves that you see are eventually getting overturned because they are unstable, right? And not just the surface wave that we are talking about. So this is the surface wave, but there are also internal waves like what you see here. This is an example of these are internal wave. Okay, and what is internal wave? So you can see that there are 3 different layers of fluid. So let's assume this is air, this is air, this is water, and this is also water, but here the density is rho 1, here density is rho 2, which is greater than rho 1. Okay, so it is salt water, but there is stratification. So now there is wave within water, right, within the same fluid. Why? Because there is density difference, and now both these layers might have different velocity. So within the same fluid also there is a chance of wave getting created, and these sort of waves are called internal waves when this happens within the fluid layer. And these internal waves are also very unstable because of this shear flow. Okay, so that is in case of ocean, which is very common. Then in case of clouds as well, like in atmosphere, you might have seen this kind of images where you see these unstable clouds. So they are still waves, but they have got overturned, right, because there is a lot of wind velocity in form of shear flow. Okay, in case in the atmosphere, and that happens because there is a lot of stratification as well in the atmosphere. Density changes as you go from lower layer to higher level, and then there is shear flow in different layers of this density, and that creates this instability, right? And likewise there are internal flows, internal gravity waves, as you can see here in cloud. These are flowing in form of waves. So these are basically internal gravity waves within the atmosphere. So internal gravity waves are not just in the oceans but also in the atmosphere, and they are bound to have this instability. So what actually happens is, whenever this shear flow brings instability in the system, it actually leads to transport of momentum, right, heat or solute. So as we saw in the last slide, it starts from the sharp interface between two fluids, but because of this instability the two fluids mix, right, and when it mixes, obviously it is losing momentum from one layer to another, or it is losing heat from one layer to another. So there is a lot of mixing of or transport of momentum, heat and solute during the process. Okay, so this kind of instability that we have been seeing is actually popularly known as Kelvin-Helmholtz instability, and it is name of the both the scientists who actually came up with this criteria for the first time. So Kelvin-Helmholtz instability is basically shear driven instability, as we have seen, shear flow driven instability, and it occurs particularly when there is velocity shear in a single continuous fluid, or a velocity difference between two fluids of different densities, right? So it can happen within a single fluid also, when there is shear flow within the fluid, or if there is stratification, or if there is velocity difference between two different layers of fluids of different densities. Okay, so but the primary criteria is there should be a shear flow. That is the major criteria for the Kelvin-Helmholtz instability to occur. Okay, and what exactly it does is, it is caused by destabilizing effect of the shear, right? So shear flow is bringing destabilization effect, so it's trying to make the system unstable, and it is trying to overcome the stabilizing effects of stratification. So basically, if you have much heavier fluid at the bottom and lighter fluid at the top, it will be much more stable, or that stratification will try to make the system stable. However, that stabilizing effect of stratification is generally overcome by the shear flow, that is the kinetic energy that comes from, let's say, the air velocity on top of water, etc., and that basically works as destabilizing effect. Okay, so this is a competition between stabilizing effect of stratification versus destabilizing effect of shear. Okay, and we will see how do they affect the instability criteria soon. And then this Kelvin-Helmholtz instability, as we already seen, enhances the transport of momentum, heat and moisture or solute in the atmosphere or ocean, right, depending on how much overturning is happening in a wave, etc. All right, so these are some examples from the atmosphere and ocean, or from the nature, but to analyze this problem in more detail, there are many theoretical or experimental work have been performed. So we are going to study the theoretical part very soon, but this is one lab experiment which have been performed to understand this instability in more detail, right? And it was performed by Thorpe in 1971. So what do you see here is a tank. Basically, this is a tank. It is a closed tank, okay? It is closed from all sides, and it has two layers. So upper layer is filled with lighter fluid and lower layer is filled with heavier fluid. Okay, so this is, let's say, row 2, the upper one is row 1, so row 1 is smaller than row 2, okay, and it has the depth of h by 2, and the lower layer also has the depth of h by 2. Okay, so originally these two layers are kept perfectly horizontal, or the tank is perfectly horizontal, right, at time t equal to 0. So you can assume that if this is x-axis, so the theta between the tank and the axis is 0 degree at time t equal to 0, right, and the interface between them is perfectly horizontal. As you can see, there is a clear interface between them, so there is a sharp interface. Okay, so what happens is, now at time t equal to 0, this tank is tilted. Okay, so this is now making an angle of a certain degree. So if this is the tank bottom surface, this is the horizontal axis, so now there is an angle theta which is greater than 0 degree. So tank has got tilted, and because of that, what happens now is, this fluid, which is basically lighter in density, it actually tries to move upward, whereas bottom fluid tries to flow downward. Why? Because the red fluid is heavier in density than the green fluid, right, and that's why the heavy fluid tries to come down and lighter fluid tries to go up once the tank is tilted. In the process, now there is a shear flow, right? So this is creating a shear flow where one fluid is moving in another direction, where and there is a relative velocity between them, and that is why it starts creating these waves. As you can see, small waves. So it starts creating these waves everywhere because there is a shear flow. And now if you keep this tank tilted, with time the wave actually amplitude increases, right? The amplitude increases, and with time this increases further and further, and you can see it starts overturning, right? There is overturning of wave, and the wave becomes so unstable, it overturns, and now there is a good mixing between these two layers, and eventually you can see there is sort of an diffuse interface between these two, right? So originally, which was a sharp interface, as you can see here, there is a clear distinction between these two layers. In later case, you cannot see that clear distinction, right? So you can see there is this mixed zone. So right, so what's happening is, because of the tilting of the tank, it starts creating wave due to the shear flow, and that shear flow actually grows the size of the wave in terms of amplitude, and slowly it overturns, and eventually that converts these two layers into a mixed layer. Okay, so this is a lab experiment that has been performed, and obviously there are many more studies after this initial study, and now, having seen the instability both in the atmosphere and in the wave, and with lot of evidence that this instability is very common in nature, we will try to understand its behavior mathematically, and we will try to find the stability criteria for this kind of flows, and we will see how, in what kind of cases these waves grow longer, or how it becomes more unstable, in what kind of cases these waves are more stable. So we are going to analyze all these cases mathematically.